In this video, we'll discuss two other operations that are useful to have in a convolutional neural network for solving harder object recognition problems. So the architecture that have been described so far, where we have convolutional layers followed by pooling layers and pooling subsampling layers that alternate before we reach some output layer, gives a neural network that actually works really well for somewhat simple problem like handwritten character recognition. In fact, such architectures have been used for reading checks in the US with a lot of success. But it turns out that when we apply it on a harder problem like object recognition of the type that we find in the Caltech 101 dataset, for instance, where we have a lot of background variations and a lot of variations with respect to the appearance of the objects, and we have colored images and so on. Turns out that these types of networks actually perform not so well with this particular architecture compared to other more standard approaches in computer vision. But to get better performance, we actually need to introduce two other operations which we'll describe in this video. The first operation is very simple. It's called the rectification layer. And it consists of taking the previous layer and just computing its absolute value, and that becomes the new layer. We will usually do this rectification right after the convolutional layer operation. And one advantage that it has is that it introduces invariance to the sign of the unit of the previous layer. And so, for instance, if we have a feature map that computes the activation of something like a filter of connections that look something like this, so that's looking for high intensity here and low intensity here. Well, if we have an edge that's, if we apply this filter around an edge which has high activation here and low activation here, it's actually going to have a large but negative sign when we perform the convolution and we compute the pre-activation. So by taking the absolute value, it means that we will now lose the information about whether the polarity of the edge was high intensity, low intensity, or low intensity, high intensity. We'll confuse the two. And if we think that detecting certain objects is actually invariant to the polarity of the intensity of the pixels across edges, then this is a kind of operation that should be useful. And for object where the actual color of the object might not be that informative, for instance, we can imagine that something like this is actually useful. And the second operation we'll introduce is called a local contrast normalization. So we have a layer that just computes that. The local contrast normalization, I give the full equations here, but I think I'll just describe intuitively what it means, because just the description should make it clear what it's performing. So we just take the previous input, the previous layer, and then we subtract some local average, which is computed locally in some neighborhood, and we can also compute the average across the channels of the layer. So this is illustrated by this sort of little 3D cube here that goes across the filter maps. So we might have an average that is computed across feature maps, or I guess input channels, if we're considering this to be the previous layer. We're treating it as input channels. And then we just take the local average and subtract it. So that's what I'm calling Vijk. And then next, we'll actually divide it by a local standard deviation. So we're taking whatever value that we centered using this local average, and then divided by a local standard deviation, so we just take our centered values, we take the squared, use the same weighting that we use for the local averaging here. We take the sum of the squared and then apply the square root on top of that sum. So this is a standard deviation because we're taking the some average of the square difference with the average, and it's local because it's only computed in some neighborhood indexed by P and Q here, where we see that we have applied the offset here. So we divide by that. The max with C is just to make sure that if we have a standard deviation that's 0, we don't actually divide by 0 and get numerical problems. So what this is doing is that it reduces the unit's activation if its neighbors in the local neighborhood are also very active. And so it's sort of encouraging competition within a neighborhood of a single feature map, or even across feature map. If we're allowing to take our local average across feature maps, then we're actually also encouraging competition across feature maps, so that these different features perhaps try to learn instead things that are different. And one thing it can also do is that it can introduce some normalization with respect to local changes in the illumination, because illumination will essentially just change the scaling of the intensity of the pixels. And so by dividing by this the standard deviation, we essentially get to cancel out the impact of the illumination in the computation of the original feature map. Okay, so that's another operation that's very useful for convolutional neural networks. So these two operations here are usually introduced between the convolution and the pooling. So we introduce them right here. And to finish up, other types of preprocessing that's useful directly on the images is to, well, first convert them to grayscale if we think that color information is not useful for detecting the objects we're interested in detecting. Often all the images are resized to the same canonical size. So 150 by 150 is something that's often used. And then we use zero padding for the images that are not squared, so that they cannot be, so when we're resizing, we want to respect the aspect ratio of the original image, so we apply some zero padding to get the same aspect ratio. Often we remove the intra-image mean, so the mean of the pixels within the given image, and divide by the standard deviation also of that image. So that will also make us more invariant to illuminations, variations in illumination in the images. And often we also apply local contrast normalization, so that we get also some amount of invariance to local variation in the illumination in the scene where the image was taken. So those are the other two types of layers that we often add, as well as preprocessing, that are useful to get a good system, object recognition system for using a convolutional neural network.